Good morning, everyone, and welcome to this lecture. This is rotation lecture number 8, and we are supposed to discuss angular momentum. I think we had discussed angular momentum of a body, of a particle about a point, and we had done some really good questions on it. Remember this question that we did, where we found out the angular momentum of a projectile at any time, and we found out the most general way of doing it. Do we remember this? The most general way of doing it, and this is the formula that we got. Remember this. I'm expecting questions from this. I also have your previous year papers, and I was just looking at them, and I will solve some problems from there as well up till this point, and see, and you will understand that whatever problems we are doing, same problems even with the same language will come in the examination hall. So if you just concentrate on what we are doing in the class, and the sheet that I've given you, that is much more than enough. Apart from that, if you get time and if you get questions from outside, that is what you need to do. If you want, you can also get a book on the previous year question papers for additional practice. That is all that you need to succeed. We had seen that angular momentum of a rigid body about a fixed axis can be written as I into omega, but remember it's an actual equation. It can only be written along the axis of the rotation. I hope you remember this, yes or no? Eh?
Yes, sir.
Okay. Now, now remember this chapter rotation is quite vast and quite big, and lots of things are there. And remember what we are doing now, we have to do it again. But what I'll do is we'll start with this. Now we have seen what angular, we have seen what is angular momentum, and we have seen that the rate of change of angular momentum is the torque, yes or no? So we will start from that point, and we will start with this theorem, and we call it angular momentum. Oh, sorry, not angular momentum. Angular impulse. Angular momentum theorem. Now, what is this angular impulse, angular momentum theorem? Now, if I go, we had seen the rate of change of angular momentum dl by dt is your tau, yes or no? So I can write this change in angular momentum dl is tau into dt. Now, if I find the total change in angular momentum, that is known as the angular impulse. So if someone asks you what is angular impulse, your angular impulse j vector is the change in angular momentum, and this angular impulse is doing the same job as what? This angular impulse is doing the same job as what? Huh?
Impulse, sir.
As impulse was doing in, as impulse was doing in that linear motion. Angular impulse is going to do the same job as impulse was doing in linear momentum. In linear motion, not linear momentum. Linear motion. Do we understand this? Yes or no?
Yes, sir.
So angular impulse, again, it's a vector quantity. And what type of vector it is?
Axial.
It is again an actual vector. You can find out its unit, SI unit. Torque is SI unit is Newton meter. So it is Newton into meter into second. You can find out what is this. This is angular impulse. Now, if I don't use vector, I can write, because things are only going to rotate on one axis. There is no point of using vector. So if I don't use the vector sign, I can write impulse as change in change in not momentum, change in angular momentum, and that is nothing but integral of tau into d theta, tau into dt. Now, since it is integral of tau into dt, if I have a graph between what? Tau and t. If I have a graph between tau and t, the area under this graph will give us the change in momentum, or change in angular momentum, or it will give you the impulse. So impulse J, angular impulse J, or change in angular momentum is area under tau t graph. Do we understand this? So this is exactly same as what we had done there. If we draw a force time graph, the area under force time graph gives us the impulse or the change in linear momentum. The area under tau t graph gives us angular impulse or the change in angular momentum. Do we understand this?
Yes, sir.
Have you noted it down? Okay, I'll give you 2 minutes. Once you're done, please let me know.
Sir, it's done, sir.
Everyone?
Yes, sir.
Okay. Then when I wrote this statement, change in angular momentum is equal to impulse. This statement, or this definition of angular impulse, is basically known as your impulse or angular momentum theorem. The change in angular momentum is equal to the angular impulse. This statement is known as angular impulse theorem. Do we understand this?
Yes, sir.
So whenever I say angular impulse, the definition of angular impulse actually tells us the angular momentum theorem. Everyone understands this?
Yes, sir.
Please note it down. This is angular momentum theorem. Angular momentum theorem. Noted it down, bacha.
Yes, sir.
Now, we can now do a special case of this angular momentum theorem. What is the special case of this angular momentum theorem? I will call this angular momentum theorem as the mother theorem. Now, you might have remembered this term mother theorem that I've used. Where did I use this mother theorem term?
It's work energy theorem and lock me.
Work energy theorem and Locke. I use work energy theorem in linear motion work power energy. And there I use the lock may. I again use this work energy theorem in rotational motion, where I also included the rotational work. Yes or no? Do we remember this?
Yes, sir.
So I use this mother-daughter theorem in work power energy, in work energy theorem, work kinetic energy theorem, as well as I used it in rotational motion for rotational kinetic energy, rotational work. Anywhere else? Anywhere else did I use this mother and daughter? Did I use this mother and daughter anywhere else? Mother theorem applicable everywhere. Daughter theorem only applicable in certain cases. Huh?
That's it, sir.
That's it. That's it. That's it. Nowhere else we use it. Okay, then that would be it. Probably I remember it wrongly. So the next heading that we will write is known as law of conservation of angular momentum, and I will call it low cam. Law of conservation of angular momentum. What is this law of conservation of angular momentum? Now, I had seen that dl by dt vectorly is tau. Now, if tau is zero, then what will happen? If tau is zero, implies the change in angular momentum is zero, or I can say angular momentum remains constant. This law, my dear friends, is known as the law of conservation of angular momentum, which strictly says that if the tau acting on a body is zero, then the angular momentum of the body remains constant. This law is known as the law of conservation of angular momentum. And you can understand that this is a special case of what? This is a special case of what? This is a special case of angular momentum, angular impulse theorem. This is a special case of angular momentum angular impulse theorem. Therefore, this theorem will be known as the what?
Daughter.
Oh, we remember it. See, God is great. I always believe that God exists. Sometimes my faith gets shattered. Oh God, what is going to happen? World is going to end. But then that faith is restored. That this is known as the daughter theorem. This is daughter because it is a special case of mother. It cannot be as good as the mother, but it is quite good. So this is the daughter theorem. Then what is the mother theorem?
Angular impulse, angular momentum theorem.
Did we hear it before? Did we hear this before? This daughter mother relation did it come before? It came in linear motion also. Linear impulse momentum theorem. Impulse momentum theorem is the mother theorem.
Yes, sir.
Law of conservation of linear momentum is the daughter theorem. She cannot do everything. Mother is always good. Mother can do everything. She can cook, she can go to office, she can do this, she can do that. Daughter can only study and do nothing. That is what the daughter is supposed to do. Study. Impulse momentum theorem. Angular impulse, angular momentum theorem. There are only 2 or 3 theorems in the entire mechanics, my dear friend. 2 or 3 theorems. What we have studied. F is equal to ma. Half of the physics goes in F is equal to ma. Law work energy theorem, 30% goes there. Whether it is rotational work energy theorem or transitional work energy theorem. Whatever remains 20% goes in linear angular impulse, angular momentum, or law of conservation, because these are all mother-daughter. Only those 3 things you have to understand, my dear friends, and you're taking so much of time. Anyways, this is what angular impulse, angular momentum theory is all about. It is exactly the copy of the impulse momentum theorem of linear motion. Now, this equation is written vectorly, but sometimes this the net torque may not be 0. The net torque may not be 0, but you might have torque about one axis as 0, one point as 0. Then you can apply this daughter theorem in different axes as well. So if total tau is not 0, net tau vectorly is not 0, but tau about any axis is 0. About any axis on any point, you can see, oh, the torque is getting cancelled. Then you can apply this impulse momentum, this angular impulse momentum theorem, daughter theorem. That means this law of conservation of angular momentum, locam. Can apply this locam along that axis. Yes, angular momentum along that axis will remain constant. Do we understand it, or this is going above? I think bye bye. Bye bye. I'm going. Don't worry. Huh?
We understood, sir.
So sometimes you might find a case where angular momentum is not conserved vectorly, but it is conserved along an axis, and the best example for this could be given by this problem, not a problem, this one. If you have this conical pendulum, do you remember conical pendulum?
Yes, sir.
This conical pendulum, this is your conical pendulum. This is your conical pendulum. This conical pendulum, you have this dung, 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 dung. It goes like this, then pung, 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 pung. It comes like this. This is a conical pendulum. Now, in this conical pendulum, it is coming out from this point, let us say. It is coming out from here with a velocity v, and it is going inside from here, let us say, with a velocity v. Now, arey, yaar. Okay, so it is going inside with a velocity v. Now, in this conical pendulum, if you draw the free body diagram anywhere, let me not draw v here, because then the free body diagram will look, I hope you understand the meaning of this, yes or no? That v is coming out from here, and the body is going here. Do you understand this?
Yes, sir.
If I draw the free body diagram of this body, the weight mg is downwards, and the torque and the tension T is like here. It is pointed towards the center. Yes or no?
Yes, sir.
Now, if I take, let us say, point O. Now, the tension will pass through point O. Yes or no?
Yes, sir.
So the torque of tension is 0. Yes or no?
Yes.
But if I find out the torque of the weight mg about O, it is not 0. because there are infinite number of axes that can pass through O, and one of those axes is the axis which is perpendicular to the plane of this. Do we understand this?
Yes,
So
sir.
torque of the weight is not zero about the point O. Do we understand this? Torque of tension is zero about the point O, but torque of weight is not zero about the point O. But still there is one axis about which the torque of weight is zero. And what is that axis about which the torque of weight is zero? This axis which is parallel to this weight. About this axis, now this axis passes through the point O. Therefore, torque of tension is already zero because it is cutting. The torque of weight mg, because this is parallel axis, no force can create torque about an axis which is parallel or which lies in the same plane. Do we remember this? Because they will cut somewhere. Force can only create torque about skew axis. Do we remember this? Skew axis, skew.
Yes, sir.
It has gone above and saying bye bye. Bye bye sir, nikal gaya. Okay, it's there. So here the torque is not zero about the point O. Here the torque is not zero about the point O, but torque is zero about this axis.
Yes, sir.
Do we understand this?
Yes, sir.
So about this axis, torque is zero. Torque about this axis is zero. And therefore, angular momentum about this axis will remain constant. Do we understand this?
Yes, sir.
Now, if I draw the direction of angular momentum about this point, the angular momentum is actually turning like this. Ding, 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 ding. Now, this angular momentum can be resolved into two components. One component along the axis and one component perpendicular to the axis. This perpendicular component is continuously changing. Do we understand this?
Yes, sir.
And it is changing because of the weight. But this component always remains constant. And that is why angular momentum is conserved along this axis. There's only one axis along which this angular momentum is conserved, and which is this axis. Do we understand this?
Yes, sir.
So this is an example of torque actually not zero, but you can find an axis about which that torque is zero. And you can conserve angular momentum about that axis only, no any other axis. Got this?
Yes, sir.
Got this? Because this question can come as a conceptual question. Torque is conserved about point O. There might be an option. What point O? About this axis. It is not conserved. It is not conserved this and that. Okay? Do we understand this?
Yes, sir.
Okay. Now, there would be a lot of questions where you would have to decide whether, or you will have to find out, not decide. You are not going to decide it. You have to find out whether angular momentum is conserved, whether linear momentum is conserved, what is conserved and what is not conserved. So in this question, what is conserved and what is not conserved? In this question, what is conserved and what is not conserved, because that is what you have to understand. If you understand what is conserved and what is not conserved, it is, if it is conserved, about which point or which axis or which condition it is conserved, about which point or which condition or which axis it is not conserved. If you understand this, rotation is as simple as anything in the entire universe. If you don't understand this, hey, you will face trouble. Yes, my dear friend, what is conserved and what is not conserved? Think about it. I'll give you 2 minutes. I've told you what I had to tell you. Now you have to tell me. There are only two things that you have to think about: conserved and non-conserved. Linear momentum, angular momentum. Linear momentum, angular. Think about it. 2 minutes you have.
So, what is your question, sir?
What is conserved and what is not conserved? There are only two things that are conserved or not conserved. What are those two things?
Conical pendulum, sir.
Yes. In the case of a conical pendulum, uh, ball is moving with a uniform speed. Dung, 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 dung. What is conserved and what is not conserved? You understand the meaning of what is conserved and what is not conserved?
Yes, sir.
Kinetic energy, you can also kinetic energy, rotational kinetic energy. So more the things that you understand, the better you are going to become in rotational, because most of the questions that are going to come will be based on concept of rotational motion rather than the numerical part. In the numerical part, most of the questions from rotation will come from moment of inertia. Do you understand what I'm saying? Most of the question will of numerical part will come from moment of inertia, and from all these parts you what might have what only theoretical questions. So here is the chance to become a hero. Tell me what is conserved and what is not conserved. Think about it. Remember, this is a legitimate question, which I can tell you, if I ask even the greatest of teachers this question, they might get confused. If I ask them how is the angular momentum about the point O, many of them will fall flat. Hey, what is this? We have not heard about this. Remember, no one understands rotation. No one, not even I. What is conserved, what is not conserved, and why it is conserved and why it is not conserved. So if you understand the reasoning, well, we are done. We have 2 minutes. 2 minutes to show your talents, else I will show mine. What is conserved, what is not conserved, why it is so and why it is not so. As simple as this. This is probably the best example. Probably. Is the question clear? Huh? Do we understand the question, or we are just doing अगर अक्कर बक्कर बम्बे वो 80-90 पूरे 100?
We understood the question, sir.
100 में लगा धागा. Do you have this jingle in Hyderabad? Akkar Bakkar Bombay wo? Or this is only North Indian stuff? One more minute left for you. Okay, so shall I do it? Now comes my turn. अब आई मेरी बारी. Or shall I give you more chance to do more things? Or do you think it's enough?
No, sir, we are not getting.
Not getting. Okay. Okay. So you're not getting what? What is conserved and what is not conserved? Torque vectorly is not zero. So angular momentum vectorly is not conserved, not constant, not conserved. But we can find an axis about which the torque is zero. Therefore, angular momentum is conserved about this axis. This is what you must understand about the angular momentum. Angular momentum is not conserved. Now, the next thing, if I talk about the linear momentum P is m into v. It is also not conserved. Why it is not conserved? Even though the velocity ka magnitude is same, the direction of velocity is continuously changing. Therefore, the linear momentum is also not conserved. So this is a case where the linear momentum is not conserved, the angular momentum is not conserved, but angular momentum is conserved about a given axis. If you talk about kinetic energy, it's a transitional motion. Is kinetic energy is conserved. Is kinetic energy is remaining constant because the magnitude of velocity is not changing. Why is the direction of velocity changing? Who is changing the direction of velocity? So if I draw the free body diagram, you will see that if this is theta, this will be your t cos theta, this would be your t sine theta, and this was your mg. Your mg and t sine theta are balancing out each other. Your mg and t sine theta are balancing out each other, and because of this t cos theta, your momentum is not getting conserved. Because of this t cos theta, your direction of velocity is continuously changing. So here momentum is not conserved. Angular momentum is also not conserved, but it is conserved about one axis. Kinetic energy remains constant because it is moving with a constant speed. That is what you have to understand. I hope you understood this. Note this down and remember it. Let me know once you are done. Do we understand this, what I said?
Yes, sir. Completed, sir.
What was the doubt in your mind that you could not understand this? Tell me that. In this question, what was the doubt that you did not understand? Which part you did not understand?
Sir, L vector ले sir.
L is changing in magnitude. L is not changing in magnitude. It is just changing in direction. You can write this if you want. L is not changing in magnitude. It is only changing in direction. Only changes in direction. L does not change in magnitude, it only changes in direction. Here along the axis, the direction is always constant. It is not changing, and therefore it is conserved. Is it clear now?
Yes, sir.
No doubts on this one at least?
No doubt, sir.
Okay. So now that is what you need to understand, what is conserved and what is not conserved. And let me give you some examples and you try to understand what is conserved and what is not conserved. Let us imagine that there is a rod which is not hinged, it's not fixed. Now, if I apply a force F here, and if I apply a force F here, equal in magnitude and separated by distance, what is conserved and what is not conserved? And we are not talking about kinetic energies here because kinetic energy depends on whether the collision has happened, which is elastic or non-elastic. I'm just talking about momentum and angular momentum. I've applied two forces of equal magnitude on both sides. What is conserved and what is not conserved? And I'm only talking about momentum and linear momentum. Angular momentum and linear momentum. Yes. What is conserved, what is not conserved? For this rod. You understand the question now?
Yes, sir.
What is conserved and what is not conserved? It's not such a difficult question that you have to think so much. Either you know it or you don't know it. You don't have to think so much, beta. It's a simple question. What is conserved and what is not conserved? That's simple. When is what conserved, you know it. So you just tell me the answer. Don't have to take eons to give me the answer, beta. Don't have to take a lot of time. Because if you're taking a lot of time, that means you have not understood the concept. You will not get the answer if you think for 10 minutes.
Sir, linear momentum is conserved.
Okay, well,
Momentum is not conserved.
why? I'm
Sir,
just only concerned about these two things now.
about the center of mass, sir.
What?
About the center of mass of rod, it is like net force is equals to 0. So linear momentum is conserved. Net torque is not equals to 0. So angular momentum is not conserved.
So here the net force is 0. Net force, as you can see, is 0. There is no net force on the system because both these forces are cancelling out each other. So the net force is not 0. So the net both the forces are cancelling out each other. So the net force is 0. Therefore, your angular momentum, linear momentum is conserved. Force is 0. Momentum should remain constant. Your linear momentum is conserved, but your torque is not 0. Your torque is not 0. So your angular momentum is not conserved. Do we understand this? Yes or no?
Yes, sir.
Okay. Now, the next question is, since the angular momentum is not conserved, this rod will rotate. Yes or no?
Yes, sir.
About which point will this rod rotate?
About center of mass, sir.
Remember, if any body is free to rotate, it will always rotate about the center of mass. So it will rotate about the center of mass. This is one concept that you must remember. It is going to rotate like this. If any body is free to rotate, remember this. If any body is free to rotate, it will rotate about center of mass axis. Can you easily see it? This one, if I throw it, tung 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 tung, see it is rotating. Tung 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 tung. It is rotating about the center of mass. Yes or no?
Yes,
If
sir.
I put it like this and if I give it a push like this, it will rotate about the center of mass. Anything that is free to rotate will rotate about the center of mass. In this case, case number 1, the momentum, linear momentum P is conserved. Yes or no?
Yes, sir.
But the angular momentum L is not conserved. Do we understand?
Yes, sir.
Let me make the second case. This is the second rod. I apply F here and I apply F, same line. What is conserved and what is not conserved?
Both are conserved, sir.
In this case, both are conserved. P and L both remain constant. Do we understand this? Yes or no?
We understood, sir.
Hmm. What is conserved? What is not conserved?
Sir, linear momentum is not conserved, but angular momentum is conserved, sir.
So it is not going to rotate. If it's not rotating, it's not going to rotate. Do we understand this, or this is going above everything? Why? Enough. We are done. So remember, if you understand the concept, angular momentum is constant. P is not constant. If you understand the concept, this case.
Both are not conserved, sir.
So it is going to move as well, it is going to rotate as well. Do we understand it? So this is gone above saying bye bye, bye bye, sir, bye bye, bye bye, bye bye. Okay. See, once you understand what is conserved and what is not conserved, the rest of the question becomes pretty simple. You just have to understand what is conserved and what is not conserved. Energy depends on whether the collision is elastic or not elastic. If the collision is elastic, energy is conserved. If the collision is inelastic, energy will not be conserved. So we are not much concerned about energy, because energy we know it will be given whether it is elastic or not elastic. Hmm. Here, now just change the scenario. Instead of applying a force, I am now making balls to collide. Two balls collide like this with a rod. Whether the collision is elastic or inelastic, forget about that. If the collision is elastic, kinetic energy is conserved. If the collision is not elastic, kinetic energy is not conserved. What about the other things that we are concerned about? Yes, what is conserved and what is not? Huh?
Sir, linear momentum is conserved, but angular momentum is not conserved.
And how is this rod going to rotate?
About center of mass, sir.
Do we understand this, or this is gone above saying bye bye? Bye bye. So linear momentum is constant. Angular momentum not constant. Case number 2. What is conserved? What is not? Any answer or no answer? Huh?
Sir,
No
both are
answer?
conserved.
Huh?
Both are not conserved, sir.
Why? Just like that, sir.
No, sir. Here
Yes.
at the top of the rod, momentum is more, sir.
Okay.
Below the rod, momentum is less. So impulse will be less in the downside and more in the upside, sir.
So okay. Now, whenever we are talking about what is conserved and what is not conserved, one thing you have to also understand, what is your system that you are taking? What is the system that you are taking? For example, my dear friends, if I take this only this green ball as my system, if I only take this green ball as my system, and then I ask this question, what is conserved for this green ball? Now, remember, this is a particle, so it does not rotate actually. It only moves transitionally. Is the momentum of this green ball conserved?
Yes, sir.
Before the collision and after the collision, momentum is conserved for this green ball. The ball is going to collide with the rod. Before the collision and after the collision, is the momentum of this ball conserved? Huh?
No, sir. Some of the energy is
Some of the energy, forget about energy. Energy has got nothing to do with collision. It has got to do what type of collision it is, whether it is elastic or inelastic. Forget about that part. I'm talking about momentum. Momentum has got nothing to do with energy. Energy is lost or not, momentum does not matter. Is the momentum of this ball, green ball, conserved or not? It is moving like this, and this is a rod. Ding, 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 ding. It is going to collide with this rod. Is the momentum of this ball conserved?
No, sir.
Why it is not conserved? Because there is an external impulse coming onto it from the rod. Yes. or no?
Yes, sir.
There is an external impulse I coming from the rod. So the linear momentum of this green ball is not conserved. But at the same time, if this rod is giving this impulse, this ball is also not sitting and okay, you give me impulse and I will sit quiet. Impulse is also a force. So if the rod is giving the ball impulse, the ball is also doing something now. What is that ball doing? Ball says, take it back. Whatever impulse you take, action, reaction, action, reaction. Now let us come to the second point. This legendary blue ball. Tung 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 with music. Now the same question comes here. Is the momentum of this blue ball conserved?
No, sir.
Huh? No, sir. Okay. No, sir. Why it is not conserved?
Same scenario will be applied, no, sir. Like,
So this rod is giving it tadak. Let me call this as I1, I1, so that they become different. So this ball is saying, hey, I2. But patak. The linear momentum of this ball is not conserved. But when this rod gives patak to the ball also gives patak to the rod. Remember, when your father is slapping you, he also gets hurt. The only thing is he slaps you at the part where you get hurt more rather than his hands. And so, if someone is slapping you, he's also getting slapped. I hope you understand the logic behind it, na? And that is why I ask him to slap at your harder parts where you might not get hurt so much, but he might get hurt a lot. So this rod gives a slap to the ball also gives a slap to the rod. So the momentum, individual momentums of this ball is not conserved. Yes or no? Yes or no?
yes, sir.
Now let me take any two as one system. If I take, and this rod will be yellow. If I take this rod and one of the balls as my system, is the linear momentum conserved? For example, if I take this yellow rod and the green ball as my system, is the linear momentum conserved? Well, it is not conserved because on the yellow rod, we have this I2 coming from the Uparwala ball. So the linear momentum is not conserved. But when I take what? These three things as one system. Ting, 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 ting. Now, when I take these three things at one system, and then I look at what is the external force on the system. We are not talking about weights here because during a collision, weight is not an impulsive force. Now, when I take these three as one system and then I look at what is the net external force on the system, is there net external force on the system?
No, sir.
Therefore, the linear momentum of these three taken together is constant. Do we understand this? These three things taken together, the linear momentum is constant because action and reaction forces equate each other. Action and reaction impulses equate each other. Do we understand it? Or is it gone? Right, sir, it is gone. Bye bye.
Understood, sir.
What about angular momentum? Now, angular momentum of this system, is it constant or is it not constant?
It's not constant, sir.
It's not constant. Why it is not constant? Who is going to create angular momentum? There must be a force that creates a torque. Yes or no?
Yes, sir.
Now, again, if you take all the three, all the three as one, all the three as one, all the three as one, do you see any external force? Net force? Whatever torque this will create, this will cancel that torque. Yes or no? They are equal and opposite at the same point. Yes or no?
Yes, sir.
Whatever torque this will create, this will cancel, equal and opposite. Yes or no?
Yes, sir.
So the angular momentum is also constant. Both are constant. Then if this is the case here, sir, why in the first case you wrote this as constant? Because I wanted to confuse you. Because what you thought is this case is similar to the case that we did at the top, but they are not the same case, bacha. Here in the top, I was applying a force. Bodies were not colliding. Do you understand what I'm saying, bacha?
No, sir.
This case, this is the case that you saw here. I applied two forces here. This is the case that you saw. Yes or no?
Yes, sir.
And looking at this case, you gave me the answer for this case. Looking at that case, you gave me the answer for this case. Yes or no?
Yes, sir.
But that case is different. This case is different. In that case, I applied a force. Here, I'm not applying a force. Bodies are colliding. Boom! Impulse is there. Do we understand this? So this case is also not same. Therefore, this case and the case number 2, they are same. So here also, do we understand? Here also, angular momentum is constant. Do we understand it? Or this has gone above? I think, bye bye हो गया. ये तो गया ऊपर से. Do we understand this?
Yes, sir.
And this rod is going to rotate about this point. So you can take the angular momentum about the center of the mass and you can equate it.
Yes, sir.
See, rotation is all about rotation. Everything rotates. Your head also rotates. But if your head remains still, and you understand the basic concept, the net force is zero, momentum is constant. If the net torque is zero, angular momentum is constant. That's simple. That is what I'm trying to make you understand. Here, there are action and reaction forces there, acting on the system. In the previous case, there was only a force. There was not a ball, there was not a body that I can take it as a system. Do we understand this? And that is why the angular momentum was not constant. We're only talking about the rod. Here we are not talking about only the rod. Rod and the two balls is one system. If only rod would have been the system, that this case is same as the previous case. When does this case become same as the previous case? This yellow case. When does this yellow case become same as the previous case? When I only take the rod as one system. Do we understand this?
Yes, sir.
But when I take rod and the balls as one system, the case is different. So everything depends on what system we have taken. So whenever we talk about angular momentum, so that's why I just in the beginning I just kept on writing angular momentum is constant. So that is how the books will write it and you will not understand. But you have to understand it depends on what system are you taking. Do you understand this? Huh?
Yes, sir.
Now, if you understand these things, writing the equation is a baby's job. Any baby can do this. To understand this, what is remaining constant and why it is remaining constant, that is it. Can I move on to the next one? Do you understand this or is it going above our heads? So bye bye ho gaya. Everything is bye bye. You understand this?
Yes, sir.
Now comes the next one. And in this next one, what has happened is this rod is hinged at this point. I have hinged this rod, but now the same scenario happens. A ball of mass m moves dumb. Energy remaining constant or not, that is a different scenario altogether. So don't worry about that. Elastic or inelastic. This ball comes down and now these two balls may get embedded in the rod. They might not get embedded in the rod. That is immaterial. That only tells us about the energy part. Forget about the energy right now. What is conserved and what is not conserved and why? And why? And why? And why? What is conserved and what is not conserved? And what system are you taking for that conservation? That is also important. All these are questions, beta. Trust me, all these are questions that we are solving. We are just not writing the equations. That's it. Do we understand this?
Yes, sir.
All these are questions that we are solving. We are just not writing the equations. And then in the next class, we'll just write the equations and we are done. What is conserved and what is not conserved? Fast, fast, fast. There are one or two more cases that I need to do and then we're done. Yes, what is conserved and what is not conserved? And what system are you talking about? You have 2 minutes to show your talents. Else I'll show mine. Yes, bacha. You should not take so much of time to give me the answer for this one.
Not getting, sir.
That is the simplest answer. Not getting, sir. That is the simplest answer. The not getting. Please solve. What is the difference between this case and the second case?
It is hinged, sir.
So what difference does the hinge make? If you understand that difference, you are done. What difference does that hinge make? Huh? What difference does the hinge make? No difference. You just put a nail and you hinge it. What difference does it? Huh? It makes a difference now because if even if I now take all these three bodies at one system, there is still an external force acting on the system. What is that force? What is that force? That force is coming from this hinge. It is not allowing the rod to move. It is stopping out. Don't move, your rod. You just have to turn. Don't move. So this hinge is giving an external force on the system, which cannot be cancelled by anything. The three bodies. And therefore, the momentum of the system, the linear momentum of the system cannot remain constant. It changes. Do we understand this? We just gone above and saying bye bye, sir, nikal gaya to. Do we understand this? Hinge is the external factor now. This hinge is causing a lot of trouble because it is not allowing the rod to move freely now. Hey, the rod cannot move freely. You have to stay here and you have to just rotate. And therefore, the linear momentum is not constant. Do we understand this?
Yes, sir.
What about the angular momentum? Comes the next fellow. Linear and angular momentum. Let me call the hinges O. What about the angular momentum? Fast. Now, because of this hinge, external forces are coming. I am an external force. I am at the hinge. Wee. External forces are coming because of the hinge. Therefore, the angular momentum can also not be conserved because external forces are coming. Oh God, external forces are coming. External forces. But all these external forces are coming at the hinge. All these external forces are coming at the hinge. Therefore, the torque about the hinge, any axis which passes through the hinge, is zero. Therefore, about this point, when I say this point, any axis that passes through this point, about any point, about any axis which passes through the point O, torque is zero. Because all the other forces are in pairs. The force that the lower bullet is applying on the rod, it is a mutual pair. They will cancel out each other. The force with the upper bullet is applying, it's also a mutual force. They will cancel out each other. The only force which is causing trouble, which is not allowing the momentum to remain constant, is the force at the hinge, but it is applied at the hinge. So if I take the torque about the hinge, it will be zero, and therefore angular momentum will be conserved about the hinge, not about any other point, but it will be conserved about the hinge. Do we understand this?
Yes, sir.
So that is what you need to understand, that in this case, the angular momentum actually is not constant, but if you find out the angular momentum about the hinge, it will be constant. Last case. Have you noted this down, everyone? More importantly, have you understood this? What I have, I have spent an entire class on this. I hope you have understood this. Yes or no? Huh? All my effort has gone down the drain. Do we understand this, everyone? It has gone down the drain. You understood this? Huh?
Yes.
Now this is a hanging rod. Last scenario, last case scenario. And only one bullet strikes it. It is hanging, so it cannot move. So there is a hinge at the top. What is conserved and what is not conserved? And we'll start the discussion from this particular question in the next class. So tell me what is conserved and what is not conserved. Take a deep breath. Look at the question. What is your system? This rod is of length L. Mass is given as capital M. What is conserved for this? What is not conserved? Yes, my dear friends. Energy, remember, energy comes from the collision, type of collision, elastic or inelastic. Collision does not come, change in momentum does not depend on the type of collision. It only depends on whether they are external forces or not. Ding, 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 ding. Yes. What is conserved and what is not conserved? Girls, boys, 1 minute. It should not take so much of time. If it's taking so much of time, that means you have not understood the concept. What is conserved and what is not conserved? So I will take this pink ball and the green rod as my system. If I take this pink ball and the green rod as my system, what is conserved and what is not conserved? The hinge point is O. What is conserved and what is not conserved? The linear momentum is not conserved. Why it is not conserved? Why it is not conserved?
External force is acting on it.
Where?
Point O.
On the hinge, external forces are acting. What about linear momentum? What about angular momentum? Torque about the point O, because all the external forces are at the point O. Torque about the point O is 0. Therefore, angular momentum is conserved about the point O. Only about the point O. Do we understand this? Yes or no? Well, in tomorrow's class, we will see, and all those invisible forces will come and we will be able to see them. Oh, okay, this is this force. So we will be seeing those invisible forces, that forces at the hinge, that how you will be able to find out this force at the hinge. So we would be able to see them tomorrow. Take care. Have a nice day. And may God bless you all. If you have any doubts, you can come up. Remember, all of these are questions because they can come as theoretical questions. And if you understand them, this is the most difficult part of collision. This is the most difficult part of rotation. Rotation with collision. No one understands collision and no one understands rotation. And when they come together, no one understands anything. I hope we can do a better job. Even if we understand this much, it will be more than 99% of the population. Good enough. Take care. Have a nice day. God bless you all. Bye bye. Take care of your health also.